You're listening to The Solution, a podcast by Growers Mineral. I'm your host, Russell Bobel. In this ongoing series, we will be taking a look at the book More Food from Soil Science, a book written in 1965 by one of Growers' co-founders, Dr. V.A. Tietjens.
Chapter 6. The Soils That We Farm. Soils vary in their composition with respect to total available plant food, organic matter, clay, sand, silt, and lime content. They also vary with respect to drainage, aeration, and natural moisture content. All of these factors are affected by temperature, rainfall, cultural practices, and the crops grown on them. Topography has a tremendous effect on the productivity of any soil. Because any one factor can have an effect on a soil, it means that all other factors are affected as changes occur in the prevailing temperatures, the prevailing rainfall, or the lime content. Now, even the addition of 1,000 pounds of potash, in addition to supplying potassium to the crop, indirectly affects all other changeable factors in that particular soil. For one thing, it can release calcium in a soil by replacement, which could account for a good yield increase. So, when we deal with means of improving the productivity of a given soil, we have to do a lot of guessing, in spite of the fact that we supposedly have good soil tests with which to determine the nitrogen, phosphorus, potash, calcium, magnesium, iron, and aluminum, in addition to the reaction. To the scientist, soil is a mixture of materials of different sizes. To the farmer, soil is what he grows crops on. If he has a level, black soil, he can't understand how a neighbor can grow crops on a grayish-brown hilly soil. Yet, we can see high yields produced on every kind of soil, from the thinnest sand to the heaviest clay soil. When we refer to the soil as light or heavy, we do not refer to weight. A coarse, sandy soil, which we call a light soil, actually weighs more per cubic foot than a clay soil, which we call heavy. Sandy soils are easy to work with farm tools, but they have a minimum of plant nutrients. We refer to them as light soils. A high clay soil, which has a high percentage of clay in it, is a potentially fertile soil, but not easy to work with, so we call it a heavy soil. But when it comes to growing crops, it is possible to harvest as good a crop on one as on the other. If you were to place pure white sand in a bench or tub and supply a nutrient solution to it, you could grow a good big ear of corn, just as you could in a good soil. A pure sand must be supplied with nutrient and water at least every other day. It has no capacity to hold nutrients. It has practically no base exchange. In other words, some nitrogen, phosphoric acid, potash, sulfur, calcium, magnesium, manganese, boron, iron, copper, zinc, and a few others in very minute quantities, with sufficient fresh water to keep the plants from wilting, will grow a good stalk of corn with a good ear on it in pure sand. Of course, it is essential that the plants be grown in full sunlight at temperatures between 50 and 90 degrees. If you omit sunlight, you can't grow anything. Sunshine and temperatures are the controlling factors. Without them and carbon dioxide, we can't produce starch and proteins in the plant. Suppose we take a sand, such as we have in some areas near bodies of water, and grow plants in it. We can grow a fairly good plant with just water, because the sand has some nutrients in it. To grow a good plant on sand, we must add some nutrients, but many fewer than in a pure sand culture. It must be supplied with nutrients at semi-monthly intervals. It has a trace of clay and organic matter, which gives it a small base exchange capacity, and for this reason it must have 500 to 1,000 pounds of pulverized limestone per acre added to it to build up the calcium saturation. Without this, you probably would not grow much on it, in spite of plenty of other nutrients. A half inch of rainfall can do a lot of good to a crop growing on these soils. A loamy sand has a little more clay and organic matter in it. It has a higher base exchange capacity and therefore needs more limestone to neutralize its negative charges. These soils need 1,000 to 1,600 pounds of pulverized limestone per acre foot to supply the calcium to approach 85% saturation, which seems to be necessary to grow a good crop. This soil has more potential fertility and therefore need not be fertilized as good as a sand. Animal manures produce a good crop because the soil gets well supplied with oxygen and, if adequate water is available, it supports good crop growth. Because of the higher base exchange capacity, it will hold plant nutrients longer, and crops usually don't need to have fertilizer applied more than once or twice during the growing season. As soils become heavier, we have stronger buffer systems, which must be reckoned when we apply lime and fertilizer. Sandy loams are among our best soils. They have a small amount of clay and 0.5 to 1.5% organic matter in the surface foot. In the north, they may have 2% more organic matter than they do in the southern United States. Since the clays and some organic matter are chemically active and contain negative charges which readily combine with basic materials, sufficient limestone should be applied to furnish the calcium and magnesium to neutralize the negative charges. 85% of those charges must be neutralized with calcium to make it possible to grow a large yielding crop. Any saturation less than 85% makes it more difficult for crop plants to get sufficient nutrients. The more base exchange capacity a soil has, the more potential fertility it has. Sandy loam soils are usually quite fertile and, if properly processed, will produce a good crop, as good a crop as can be grown under our yearly climatic conditions. They will hold a fair amount of calcium, which will last 5 to 10 years. These soils are usually well aerated, where drainage is good, and when properly limed, they will permit water and nutrients to move readily from the surface to the subsoil and vice versa. On the other hand, they can also become troublesome if they are not adequately limed. Plow soils, originally of geological origin, form at the bottom of the furrow and are aggravated by our cultural practices. If the soil becomes devoid of calcium and is plowed at the same depth every year, these plow soils build up and become troublesome. They become very hard when dry and are very sticky when wet because the clay which has accumulated becomes hydrated as the calcium is removed during the years of cultivation. Such plow soils prevent the roots of crops from penetrating into the subsoil and thus can curtail crop growth in dry weather. The plow soil may prevent moisture from moving up from the lower depths. Fertilizer, when properly applied, need only be applied once during the season in an adequately limed sandy loam. These sandy loams are underlaid with subsoil that contains appreciably more clay and silt than surface soil. The calcium required on a sandy loam soil may be between 1,600 and 2,400 pounds to an acre foot. In a non-limestone soil, this may be multiplied by 4 or more, depending on how deep the roots will readily penetrate. If there are no limestone minerals in the subsoil, the application of 10 or more tons of pulverized limestone may be required to get maximum yields, even in years when temperature and rainfall are ideal. Sands to sandy loam soils are easy to work. They are not readily puddled if plowed slightly wet. They do not become sticky like clay soils and dry out soon after a rain. They should not be worked into too fine a seedbed in areas where heavy rains have a chance to pack the surface after a crop has been planted. Too much preparation of the seedbed will dry them out. This prevents the seedling from making a good root system. Many farmers are learning to plow later and plant immediately, in some cases delaying planting until the mid-spring rains are over. Before we go any further in this discussion, we might just stop and point out what makes up a surface soil. Each soil type has different characteristics. Stone, gravel, and other mineral additions are local ingredients. Clay and organic matter are the only two ingredients which affect our discussions of fertility. All soils have different minerals and vary in composition. In general, organic matter is high in cold temperatures and low in hot climates. Thus, the calcium requirements will vary. In general, a pound of active organic matter has 4 times as many negative charges and therefore requires 4 times as much limestone as a pound of clay. These figures are rather inexact and are difficult to compare. However, on the basis of field results, High organic mineral soils need much more limestone than clay loams. I have seen greenhouse experiments on high organic matter soils, which required 100 tons of limestone per acre to make up a soil to place in 5-inch beds to get worthwhile results. Silt loam soils are heavier and require more care in timing cultural practices. They can be puddled by working when too wet. They contain more clay, although the organic matter may not be much higher than in the sandy loams. Manure should be used only when drainage is good and organic matter is low. The lime requirement of the silt loam is only slightly higher than that of a sandy loam. The base exchange capacity is equivalent to 2,800 pounds more or less of calcium. They are well-buffered, productive soils. In acid soil areas, their lime requirement may run up to 16 tons or more per acre because there is so little calcium in the subsoil. In limestone areas, these soils can be limed with 4 to 6 tons in the surface plow layer. There is usually plenty of limestone in the subsoil. However, it's always good insurance to test the subsoil because often it is glaciated and varies greatly on the same farm. I tested soil in an orchard where one row of trees was growing fine because there was plenty of limestone in the subsoil, while the adjacent row was on a low-calcium soil. The rocks had been folded when formed, and the limestone stratum was at the surface under one row and down 50 feet on the next row. It is usually a good idea in rolling areas to take samples for testing on the hills and in the hollows. One often finds that because the organic matter is higher in the valleys and because there has been surface erosion, the actual calcium available to the crop is much higher in the valley. We have a lot of cropland that can be classified as silt loam, which, when it is adequately limed, will produce some of our large yields of corn, along with our sandy loams. This is sticky when wet and tends to bake when dry, but if a person will go fishing when it is just a little too wet to plow, it can grow 200 bushels of corn or 800 bushels of potato with little difficulties. Clay loams are difficult soils to farm. When adequately limed, they are easy to cultivate, plow, and harrow, but with insufficient lime, they cost the farmer money. They are potentially very fertile, but very often show no response when fertilizer is applied. When limed, they are easy to farm, provided that the farmer is not in too much of a hurry to get his crop planted. There are clay loams along our eastern seaboard which, when sufficiently limed, can produce 300 bushels of corn without the addition of fertilizer. I worked with a grower who had some Lenore clay loam, which in 40 years had never grown a crop. We applied 6 tons of limestone per acre and disked it into the surface to a depth of 10 inches. When we applied 2 tons per acre with a subsoiler which penetrated 2 feet every 36 inches, first in one direction, then at right angles, corn was planted that year, producing a tremendous crop. People came from 50 miles away to see it. The grower told me he sold 98 tons from 20 acres, which was close to 175 bushels an acre. After that experience, I became very much interested in rehabilitating our clay soils. Because these soils are so dense and limestone penetrates slowly, it is necessary to use a subsoiler to make the limestone penetrate faster. The subsoiler should be used when the subsoil is dry, because it tends to break up the subsoil in all directions and give the limestone a chance to penetrate into the cracks wherever there is sufficient rain to wash the surface soil down into the cracks of the subsoil. I have had many growers who were not growing over 50 bushels of corn an acre by applying from 500 to 1,000 pounds of dry fertilizer per acre, apply from 8 to 12 tons of limestone per acre, and increase their corn yields from 65 to 175 bushels. Of course, this could have been due to many things, but in each case, the application of limestone was directly or indirectly responsible for improved yields. Muck soils are the most interesting to work with. They have a high percentage of organic matter. The surface from 4 to 6 inches may be very active chemically, whereas the material from 6 inches to 6 feet deep may still be in a pickled condition. If muck beds are surrounded by soils of limestone origin, they probably are quite fertile and are fairly well saturated with calcium. If, however, they are surrounded by naturally acid upland soils, they are of little value for cropland until they have had heavy applications of pulverized limestone. A greenhouse rose grower. Muck soils are usually poorly aerated because the water table is too high. This not only brings about poor aeration, but also prevents the temperature from increasing. The result is a cold subsoil, which tends to keep the roots from penetrating deep enough to take advantage of the nutrients. Instead of having good oxidation, we found much fermentation, which produced gases that were toxic to the roots. In this case, a hole was dug 2 feet deep and a piece of lighted paper was dropped into it. Immediately, there was a flare-up from methane gas, which is a product of fermentation. Later, I found there was a relationship between the formation of methane and calcium saturation. If the active organic matter was well saturated with calcium, there apparently was a change of fermentation to oxidation because methane gas was not formed. I had occasion to investigate a muck soil which supposedly had been over-limed. 2 tons of hydrated lime had been applied on a strip of celery land. After the celery was set in and started to grow, it developed a yellow color and became stunted. According to my calcium test, there was insufficient calcium. The root growth was not normal. I applied 10 tons of limestone on a strip and worked it into the soil. It corrected the deficiency, and the celery grew much better than where limestone had not been applied. The roots grew deeper. I believe the 2 tons of hydrated lime were too active in the shallow layer of surface soil, releasing too much calcium, which was not in equilibrium with the base exchange complex. It prevented the roots from absorbing necessary nutrients needed. The roots were stunted. When the limestone was applied, it conditioned a large rooting area with a saturated calcium colloid. It is important that a pulverized limestone be used for this purpose. The finer the particle, the quicker the calcium becomes part of the base exchange complex. Each of the above soil types has modifications. In the coastal plain, there is much fine sandy loam, which is not well aerated because of the fineness of the sand. It requires more limestone than the regular sandy loam. There are also poorly drained soils. They have more organic matter because oxidation is slow, and even with higher temperatures, a certain amount of fermentation takes place. Subsoiling these soils can improve drainage and aeration and greatly improve yields. These soils are often farmed by the ridge and furrow method, which helps drainage and aeration. The general productive capacity of a given soil depends at least partially on its location, because each location may be affected by different geologic and erosional influences as well as by the prevailing rainfall and temperature. Heavy rainfall causes surface erosion, the severity of which is related to the degree of leaching. Crop production the country over is not correlated with fertility. Rather, yields in most states can be correlated with the activity of brains of people responsible for research work in the respective states. The fertility level of the sandy soils vary markedly in different locations. Hilltops in West Virginia can produce crops as good as those of the prairies of Illinois. If the slope of the hills is such that one can farm them with tractor-drawn equipment, one can, by subsoiling the tops and applying limestone when needed, produce exceptional yields. When one uses a subsoiler and tears up by circling the top of the hill and going cross-wire to the slopes, one can cause the rainwater to soak into the subsoil, where it can be stored for the future use of the growing crop, instead of having it run down the slope and carry soil and nutrients away. The limestone should be applied first, so it is partially distributed from the surface down to 2-foot depth. The limestone helps to make the soil more mellow. Then the water will soak in more readily. I have seen this practice make it possible to produce over 100 bushels of corn on the top of hills and on slopes that were almost too steep to farm. If you farm black prairie soil, which potentially is 300 bushel corn land, but is only producing 65 bushels, you have a problem which becomes very embarrassing. Here are tremendous quantities of plant food materials, and yet the crop is not producing as much as the submarginal hilltops of West Virginia or eastern Ohio could, if properly treated. The low yield can't be due to a lack of fertilizer. It must be due to some interference, deficiency, or excess of the wrong chemical. The main problem that we have on the black prairie soil is a set of factors favorable to the production of leaves and stems. In other words, we have an overabundance of nitrogen. Yes, we have plenty of fertility, but the balance is all in favor of succulence of growth, an overpowering effect of nitrogen against the storage of starch and sugar, which we need for yields of grain. Grains contain a high percentage of starch. 35 pounds of the dry weight of a bushel of corn is starch. Muck soils offer still greater problems. I have seen some very high tonnages of corn silage, hemp, potatoes, cabbage, alfalfa, and many vegetable crops come off an acre, but by and large, our yields from muck soils leave much to be desired. First of all, there are many different muck soils. I worked with 2 of these muck soils in Wisconsin. One muck had its origin in cattails, the other in grass. The cattail muck was deficient in potassium, while the other was deficient in phosphoric acid. The degree of decomposition of peat to muck, of course, determines its productivity. The degree of change from peat to muck or humus determines the amount of base exchange it will contain, which in turn determines the lime requirement. The general idea of soil composition should give us a good idea of what we have to contend with. A soil is made up as follows: round fieldstones of different sizes, red shale in coastal plain soils which usually need lime, limestone and sandstone shale, a source of some plant food material, gravel, varies with different locations. In glaciated areas, we have gravelly loams and gravelly silt soils. The gravel is a mixture of different rocks which represent many different minerals and are the source of much plant food materials, such as potassium, iron, sulfur, calcium, magnesium, phosphorus, manganese, boron, and many others. In unglaciated areas, we have very little gravel, although we may have the minerals present in much smaller particles. Sands. Coarse sands are prominent in glaciated areas and are washed out and carried by water. Fine sands are the result of further weathering and other agents of erosion. In coastal plain soils, fine sands may become poorly aerated and may require the same treatment that silt and clay soils need. Silt, finer than sand but coarser than clay, found in all soils, a source of many minerals used by plants. Clay, finer than silt, if fine enough, becomes a chemically active colloid which does not dissolve in water, the basis for base exchange and buffer activities in the soil. This makes the difference between sand culture and soil culture. All our soils, except the purest sands, have some. I like to think of it as a jelly-like film surrounding the larger soil particles. The physical condition of this film, or colloid, as most scientists call it, has much to do with the magnitude of the yields that may be expected, and probably is as much to blame for our abnormal soil problems as anything, except organic films, which may also become colloidal. Moisture. Water held in the soil is capillary, hygroscopic, or free water. This moisture makes up the soil solution and determines whether the soil is productive or not. If the soil has too much water so that it interferes with the ready movement of air, the soil becomes waterlogged and unproductive. Roots suffocate with poor drainage. Air. Every productive soil must have air. Oxygen is the lifeblood of any soil and determines the volume of growth of a crop. It is necessary to break down organic matter, and for all oxidation processes, oxidized products in the soil are efficient growth promoters. Unoxidized products in very minute quantities may be efficient plant growth promoters, but they soon become toxic as they increase in concentration in the soil solution. Gases. With good oxidation, the gas in the soil is restricted to carbon dioxide. The odor of the soil is very savory and clean. Some of the carbon dioxide forms carbonates with limestone and carbonic acid if the soil has too little base materials to neutralize it. Some of the carbon dioxide comes out to the soil to join that which is given off by the plants during the night as a result of the breakdown or release of energy from sugars, starches, and other similar products. With poor oxidation or reduction, numerous gases are formed. Carbon may form methane, proteins break down to nitrogen and ammonia, although the ammonia usually comes from nitrates or nitric acid. We may have hydrogen sulfide, a rotten egg odor commonly found in septic tanks. If you smell a handful of the soil, you will find it has a decayed odor. Sand cultures can tell us much about soils. From sand culture experiments, we know that we can grow a good plant by supplying the nutrients needed by plants through water, and we can accomplish our purpose with much less plant food material than many of us think we should supply. If we use red sand instead of white, we get phosphoric acid deficiency symptoms. Red soil is more difficult to manage than white or yellow sands because we have to add much more limestone to prevent the iron in the red sand from inactivating the phosphorus ion. So far, we have had no problem omitting organic matter. We have had 100% water-soluble nutrients. We've had good aeration, and the balance between the nutrients has been favorable. The acidity of the nutrient solution applied was between a pH of 4 and 6.8 without any harmful effects, but when the pH rose to 7.2, we began to see iron chlorosis make its appearance. The addition of large quantities of ferrous sulfate poured over the roots and sand seemed to alleviate the deficiency only very slowly, whereas if we put the iron sulfate in an atomizer and spray the foliage lightly, it corrected the iron deficiency overnight. From this, we can assume that at the higher pH, the iron was inactivated in the sand culture and could not be absorbed by the plant. But what about the foliage spray? This opened an entirely new field of applying fertilizer, which we will discuss in a later chapter. So we go back to our sandy loam soils and we grow crops with indifferent results until we check the calcium. We find that as long as our calcium is not high enough, we can't get good yields, even though we supply large amounts of commercial fertilizer. In other words, the base exchange complex, which we know too little about, and which is a godsend in our soils, is acting as a stumbling block to the nutrition of our plants. If we could remove that and organic matter, we would be back to our starting point, sand culture. Thus, what we have in our soils is a hindrance. That remains to be seen as we find out more and more about the different soils. We do know that simple sandy soil will grow plants very well providing we supply moisture and nutrients. As we get into our complex soils, we have to learn how to deal with extraneous matters rather than what we have to add to the nutrient supply. Since soils have a complexity of materials which we can't remove, our problem is to inactivate their interference, and limestone seems to do this more effectively than anything else. I built a plant grower, a wall out of limestone rock 3 feet tall around 2 sides of my porch. When we had it finished, my mason said, "I have several loads of subsoil that was left when we dug our basement hole. It isn't much good, but it might do to fill in 2 feet." So we got a load. From its appearance, any sane person should have used it for road fill. It was silt and clay, crumbly, yellow, red, and blue mottled in color, with pieces as hard as brick. I looked at him, then at the soil and said, "Okay, we will use it, but I want to mix plenty of limestone with it." We filled in 4 to 6 inches with this subsoil and put an 80-pound bag of limestone on it. This was an area 2 feet by 24 feet or 48 square feet. When we finished, we figured we had not less than 50 tons per acre of limestone on each 8-inch level of soil, and it was well distributed. We finished the load and had another 12 inches to fill. He said, "What are you going to use for the top?" I said, "Another load of the same stuff." We finished the filling on Saturday evening. On Saturday morning, when the soil was still sticky from the water I poured on the previous evening, the 2nd of August, my wife gave me odds and ends of plants from the garden, which I set in. It seemed too late in the year to expect anything from them, but by the time the frost killed most of the plants, they were a sight to behold. It was a conglomeration of plants 2 to 3 feet tall and full of flowers. No fertilizer had been applied. I did expect that the aeration the soil got from being exposed to the air with the limestone would grow good plants, but I did not expect much luxuriant growth the first year. On the basis of these observations, it would seem that our problem is to reduce interfering influences rather than to add something that will make the plant grow more efficiently. Every soil has chemically active clay and organic matter, which, in an unsaturated condition, exerts more osmotic pressure than the roots of plants can exert, with the result that soluble nutrients may be drawn and held by the base exchange complex to the disadvantage of the growing plant. This hypothesis is not valid unless we assume that some oxygen plays a part in the interchange. Certainly, oxygen plays a very important part in this type of growth that is necessary to produce a big yield of corn. According to research done by the Europeans early in the 20th century, the calcium ion plays an all-important role in the yield potential of any soil. This apparently is accomplished by having sufficient calcium supplied to the soil so that 80 to 85% of the negative ions in the base exchange complex are neutralized by the calcium. The neutralization process apparently relieves the osmotic pressure so that the plant can abstract the nutrients it needs. We must remember that an application of barnyard manure can build up additional base exchange, and it is reasonable to assume that the 25 additional bushels of corn obtained when 300 pounds of limestone are added to a yard of manure may be due to the neutralization of active organic matter introduced with it. Even plowing under a heavy green manure crop may temporarily increase the calcium requirement of a soil. Most research thinking has been done in terms of supplying more plant nutrients or introducing factors which eventually will add additional nutrients or build them up by resting the soil. The calcium needs of a crop are not large, but the soil needs are high and vary with the soil type. As long as the calcium is maintained at a satisfactory level, the soil will produce good crops. One hears the expression worn-out soil. I don't know what that means. I have an idea it means depleted of nutrients. It is an expression commonly used by fertilizer people to sell fertilizer. I have seen soil made very unproductive by the continuous use of commercial fertilizer. The grower, upon good advice, made the soil productive by adding limestone and withholding fertilizer for several years. That seems to belie the idea that soil wears out if you don't apply quantities of commercial fertilizer. The above should not be considered as evidence that fertilizers are no good. To me, it means that the people who advised this farmer on his fertilization program didn't know what they were doing. I shudder to think of the information farmers are getting from people who are supposed to know. In conclusion, I would like to note the pointlessness of some of our farm programs. As a result of 50 years of testing research that has barely maintained our yields, we have put the cart before the horse. I am giving some farmers credit for learning how to grow good crops by trying new things. With the soil situation we have in the United States and practices based on the classification of good, fair, and submarginal land staring us in the face, it amazes me that we are still maintaining surpluses of some crops. It is my honest experience that it is easier to grow big yields on poor and submarginal land than on so-called good soils. I have worked with farmers in many states who will support my thesis because of the results it has obtained.
Thanks for listening, everyone, to this episode of The Solution. If you'd like to learn more about the Growers Program or anything you heard in this podcast, visit our website at growersmineral.com. Make sure to subscribe so you don't miss another episode. Thanks. We'll see you guys in the next episode.